Assalamu alaikum warahmatullah. Welcome to this lecture number 10 and 11 for the week 10. And this is actually a continuity of the previous lecture, which was about the frequency response. We say the sinusoidal transfer function, and we also studied about the transmission of force, transmissibility in general, and which included transmissibility of the force and transmissibility of the motion from the surrounding to the system and from the system to the surrounding. It can work both ways. Now, we have studied how we can find how to find frequency response. Means uh, what will be the steady state response at a frequency, at any frequency, right? What will be the steady state response at a frequency? Then we studied uh, because of the response of a system, and if the system is not balanced, then that might transmit motion or force to surrounding or from surrounding to the system. It works both ways. So this is the second thing that we studied. Now in this lecture we are going to focus on, okay, we know that the motion is being transmitted to surrounding. Is it really dangerous? And how to eliminate that. So in this lecture we are going to study about the vibration absorber. So now we know that the motion is there's an unbalanced mass in our system, and it is transmitted to the surrounding, maybe to the floor of the factory, to the foundation of a machine. But I want to eliminate that, how to do that. And second would be, we are going to discuss about the multi-degree of freedom system. So we saw 1 degree of freedom system, we saw 2 degree of freedom system. Now we are going to look at the multi-degree of freedom system, maybe three or more. So let's start with the vibration absorber. So in mechanical system, start with the vibration absorber. If a mechanical system operates near a critical frequency, what does it mean by the critical frequency? It means the frequency is near to the resonant frequency. So if the operating frequency, let's call it let's call it operating frequency or excitation frequency. Operating frequency or excitation frequency is near to the resonant frequency or natural frequency of a system. You can say call natural frequency of a system, then the vibration amplitude will increase with the time, and it will go to extent that it cannot be tolerated. It will damage the machine, it will destroy the machine, and ultimately machine will break, theoretically. So we add damping to the system to make sure, the first thing we do is to add damping to the system so that it absorbs that vibration. But in many cases we cannot add damping after a certain quantity or up to a certain extent. We can add the damping, but we cannot be only beyond that, because the vibration is simply too large. We cannot keep on adding any dampers or rubbers or any vibration absorbing materials. We simply don't have capacity, or we simply don't have enough provision in that design or in that setup. So in that case, what we do, we add a device called the vibration absorber. So what this device do, uh, it's actually a mass spring. It itself is a mass spring system, and it increases the degree of freedoms of the system, and we'll see that. So before going into that detail, let's suppose we have a rotating machine, let's like we saw in the last lecture. So where is it? Let's say we have a rotating system. There's no shaping. Okay. So in that system there's an unbalanced mass, and that is rotating at a certain frequency. Let's say that is omega, and that system is placed on a foundation which has some stiffness and some damping. Let's call it K and let's call it B. This is a mass M. I'm calling this whole system as M, and it is rotating at a frequency omega, like we saw in the last lecture. And because of this unbalanced mass, a force is being generated. Let's call that force as P T, which is equals to P, that's the magnitude of the force, sine omega t, that's the excitation frequency. I'm going to erase this omega for now. This excitation frequency. Okay. So and let's say this is the direction of the motion for our system. Now if in any situation we have a rotating machine like this one, like a turbine, like a compressor, like a washing machine, and it's causing vibration, and it not just vibration, it produces a large vibratory forces to the machine foundation, to the machine from now a lot of vibration is being transferred to the foundation. So and this vibration is caused by an unbalanced mass that we have seen as and we have calculated in the last lecture. What if this excitation frequency, that omega, becomes equal to the natural frequency of this whole system? So in that case, obviously, the vibration amplitude will keep on increasing. It will undergo resonance, and it will ultimately destroy the system. So if in such scenario, let's say you are designing a system where you are likely to encounter an excitation force which may match the natural frequency of a system. Again, take the example of, I'm just giving a very rough example, like a bridge, and you like bridge is likely to encounter some air gust with the wind gust with some excitation frequency which may match the natural frequency of the bridge. So in that case you will add a device called a vibration absorber, and what that device will do, it will eliminate that transmitted force. And how it do it, we design the device. Let's say omega a is the natural frequency of vibration. I'm just calling it VA, vibration absorber. So the device is designed in such a way that the natural frequency of that vibration absorber is equal to the excitation frequency. So in that case, that vibration absorber absorbs that transmitted force and making sure that the force is not transmitted to the system. One more thing. Initially, system was 1 degree of freedom. What this vibration absorber does, it increases to 2 or multiple degree of freedom. That's 2 degree of freedom, let's suppose. Let's call it 2. So it increases the 1 degree of freedom to 2 degree of freedom, and if the system is 1 degree of freedom, it will have one natural frequency. If it is 2 degree of freedom, it will have two natural frequency, 1 and omega naught 2. If it's 3 degree of freedom, it will have 3 natural frequencies, right? So what happens when it increases degree of freedom? So now the natural frequency of systems have been increased, and they move far from the excitation force. So it is designed in such a way that if this is my excitation frequency, so one natural frequency is well above the excitation frequency, and other natural frequency of a system is well below the excitation frequency. So in that case, our system is safe from the resonance. And how we do it? So let's suppose the system I have just drawn, and know that here P, we have done all this calculation in the last lecture, where P can be written as, based on centripetal force, it can be written as m omega square r. That's the P, and m is an unbalanced mass. So if we want to write the sinusoidal force of amplitude, we will have that equals to m omega square r. We have calculated this one in the last lecture. You can refer to the last lecture. That's k square plus damping square omega square divided by under root k minus m omega square square plus b square omega. So that's the vibration amplitude in such cases. So what we do for the vibration absorber, I will just copy this one. So if we want to add the vibration absorber, we will add a mass spring system with the device. Let's say the dam stiffness coefficient for this system was Ka, and we have the mass equal to, let's make it smaller, Ma. And again, it has its own independent coordinates, so now we have the 2 degree of freedom system. That's Y, and we have the X, and it is designed in such a way that the natural frequency of this mass, that is under root Ka over Ma, is equals to the excitation frequency. So we make sure while designing this one that it matches the excitation frequency of our system. So if we want to write this equation of motion for this system, this new system with the vibration absorber, we will have the equation of motion for the system itself would be equals to mx double dot plus bx dot plus kx uh, plus this ka x minus y, this whole equals to, there is a force being act because of this unbalanced mass, that is pt. So it will be equals to p sine omega t, as you have seen before. Then for this mass, this independent coordinate, we will have the equation of motion equal to ma y double dot plus ka. Now y minus x, keeping this one fixed, and now we'll calculate with respect to y. It will be y minus x equal to 0. There is no external force acting onto this one, it's just absorbing. So here x and y are the displacement of mass m, capital M, and the small m, ma actually, and they're measured from the equilibrium position. Now we can take the Laplace transform for this equation. It will become ms square plus bs plus k plus ka into x of s equals to, this whole become equals to this. Now we have another one, and that is minus ka y of s equals to vs. And for this equation 2, we will have ma s square plus ka, this both into y of s minus ka x of s equal to 0. Well, let's call it equation a, let's call it equation b after this one. So from equation a, eliminating, we can substitute y of s into this one and simplify, because we want a transfer function that is the output over input, and we have input as p of s and output of the system. The actual system we have is x of s. So we can take the value of y of s from this equation and substitute in this one. You can do the maths for yourself. Now eliminating y of s, this equation will become ms square plus bs plus k plus ka minus ka square plus mas square plus ka, this whole into the displacement equals to the excitation force. So from here we can write it as output over the input force is equals to MAS square plus KA. If you just take the LCM for this one, we take the, yeah, and then we have MS square plus BS plus K plus KA into MAS square plus KA minus KA square. So, and because we are more interested in the steady state response, you're not interested in the whole response, so we have to convert this transfer function to the sinusoidal transfer function. That will become x iota omega equals to p iota omega. That becomes equals to minus ma omega square plus ka. This whole equals to minus m omega square plus k plus ka. I'm not doing the all the steps. You can, if you want to look into the steps, you can have a try, and if you have some trouble, you can always contact me. Minus ka square. So in the actual system, the free vibration will eventually be vanished because of the damping, even though it is small. And the force option at the steady state can be represented by the equation now, because as we have seen the transmission of the force, if this is force is being acting onto the system, so it is being resisted by these mass spring damper system, so the force transmitted, this force that is being transmitted is equal to this force that are resisting the applied force. So we, as we have seen in the transmission of the force, so we have F of T transmitted force equals to actually Kx plus Bx dot. But in case if our damping is really small, so this becomes 0. So the total transmission force is equal to Kx. That's a transmitted force. Now the amplitude of this transmitted force, we can write it as F of T equals to K into X iota omega, this one, so we can write it as F, sorry, so we can rewrite it as X iota omega equals to Ka minus M omega Ma omega square divided by K plus Ka minus M omega square into Ka minus Ma omega square minus Ka square. We have to take the magnitude of this one into the P iota omega. You can further simplify these equations. You can open up this P iota omega, so it will become equals to M omega square R into Ka minus Ma omega square. Just keep in mind omega is the excitation frequency. K plus Ka minus M omega square. Ka minus Ma omega square minus Ka square. So we know that the Pi iota omega was equals to M omega square R, as we have seen in the beginning. Now in this equation, if we observe one thing, that if we choose the mass of the vibration absorber and the stiffness of vibration absorber in such a way that Ka minus M omega square is equals to 0. So it means our Ka over Ma is equals to omega square, or under root Ka over Ma is equals to the excitation frequency. Sorry. Excitation frequency. So the dynamic absorber are designed in such a way that their mass and the stiffness is selected carefully, so that it matches the excitation frequency to eliminate the transmission of force. So physically, the what it means that the effect of dynamic vibration absorber is to produce actually a stiffness force that cancel out the excitation force P. So because as you have seen here, the total transmission force was based on the stiffness force, right? And only that stiffness force is responsible for opposing this P iota omega. So we design the vibration absorber in such a way that the stiffness force it produces, it should be able to cancel out the applied or the produced excitation force, or its natural frequency matches the natural frequency of the excitation frequency actually. So we can even calculate this one. Sorry, we can even calculate this one. We can say y iota omega equals to p iota omega, which is the second coordinate of the system, is equals to x iota omega divided by p iota omega into y. That's not a good one. Into y iota omega divided by x iota omega. So we can multiply these one. We will have at the end as Ka divided by minus m omega square plus k plus Ka into minus ma omega square plus Ka minus Ka square. So this is how we can find out the displacement in the absorber itself. And if the natural frequency of the vibration absorber is equal to the excitation frequency of the system, then it means Ka is equals to ma omega square. And if we substitute Ka into this, if we substitute ma omega square is equals to Ka, then we will have something at the end as if you solve this one, you will have the equation left at the end as y iota omega divided by p iota omega equals to Ka minus Ka square equals to 1 over K minus 1 over Ka. And for the total response, it will be y of t equals to, now we have to take the magnitude of this one into p sine omega t plus phi. That's our final response, and you can write it as minus p over Ka sine omega t plus phi. That's the displacement in the vibration absorber. So this is how we can find out the we can find out how to design the vibration absorber for the given system if we have such and such frequency of excitation force. So this is how we need to estimate the parameters for the vibration absorber, and you can even calculate the displacement in the vibration absorber itself and displacement after the in the system after adding the vibration absorber. So to clarify it further, let's try an example problem. Let me elect an example problem for you guys.